Okay, so so I regularly play tennis with this guy, and every single time we step onto the court, he says something like, after we exchange pleasantries, he's like, yeah, I just got back from Europe and I'm jet lagged, or hey, I'm just getting over a cold, or I'm just getting over a pulled hamstring. And it seems like he's like pre-registering his defeat, or his excuse for defeat. And I'll do the same thing right now. So I've never given this talk to anyone. I had like a brief aside yesterday with Alexander where I kind of mentioned the key things, but I pre-register this because I take I take seriously the spirit of the workshop. So my hope is that in the discussion you'll rightly smell blood and go after me so that I can make this paper better. Well, this is a paper, so that I can make the paper out of this. And so, yeah, with that, I'll jump right in. So, what I want to talk about today is this thing that I've observed, and we saw this yesterday, which is that in our discussion in the literature, in our discourse about AI and science, our philosophical discourse, we typically frame the problem as there's a scientist or an agent or often a doctor and her computer and her AI. And they're sort of they're in conversation with one another in some way or another, right? So she might be consulting an AI to make a diagnosis, you're reading the ethics literature, or she might be a scientist consulting an AI to make a prediction or a claim about some system. But this is a very sparse picture, right? It's just the person and their AI. But when you look at the science that's actually done with the aid or the assistance in some fashion of AI, these are actually projects across a lot of disciplines. You have astro, molecular biology, robotics, material science, social science. So teams, these are large teams, scientists, and the AI is situated somewhere in their process, towards the end of the process, trying to justify results. So it can be very early, and as we saw yesterday from Mario's talk, in the formulation of hypothesis. But the AI is just sort of one of a myriad number of scientific instruments and individual agents, which makes this picture look a little naive. There's a curve from one of Mario's recent papers. This is I think this is just raw counts of papers engaged with AI and machine learning from the AI and machine learning sort of section of the archive. And if you put it on a log, it's insane. But here's our curve. So this is AI and machine learning papers across all fields, 23. And this is percentage of papers, and this is hockey stick. And this is the kind of curve you don't see in nature. And then if you break it out by fields, they're all hockey sticks. Okay, so all fields. Okay, so some fields are dominated by team science. Some fields like ours are solo sports. We have a hockey stick. I know this was hard to see. This over here is a measure of the distribution of AI engaged papers over a field's journals. So you might think that all of this growth is just dominated by like a couple journals on the fringes of a discipline that are sort of hoovering up all of the publications on AI. That would make it kind of a bubble. But if the sort of AI related papers are distributed evenly across a field's journals, right, then it would be more ubiquitous. And so we just measure that using a measure of inequality. So you can use the Gini coefficient, you can use entropy. And when that's high, right, everything is pushed into a couple of venues. And when that's low, AI engagement is ubiquitous over the venues. And you can see they're all falling very rapidly, right? So AI is becoming ubiquitous, except for the curious case of history, which is rapidly marginalizing. And there's a story to be told there, but not in this one. So here are a couple slides from my colleague Logan Ward at Argonne, who's a material scientist and does AI-driven discovery of materials. And you can see scientists are involved, but as Humphrey says, they've been sort of pushed to the margins. In the middle is this weird computer brain thing. And what's happening here is this is a design schematic. This is a Department of Energy slide. It's not classified, but it's not the kind of thing you usually see in philosophy. But look, you've got a supercomputer, which is out there on the margins. You have a big data facility, which is out there on the margins. You have a beamline. That's the accelerator at Argonne. You've got actual robots that are doing things. There's people, and then there's prior knowledge. So things that we know that are sort of distributed through the literature, right? So this is knowledge that's readily available, easily available to us. And this all goes into this design engine, whatever that is, which is, spoiler alert, it's a generative model. Here's an actual workflow for how this all goes. A little red box around human in the loop, just to assure us that there's some epistemic agent that's not an AI somewhere in this. It's typically in the generate tasks, right? So that's prompts. Come up with something for the big engine to do. Okay, so this picture here, this is actually, and again, we saw this yesterday. This is actually what AI in science looks like. Of course, there are smaller sort of instantiations, but this is big science. This is again the Aurora supercomputer up there, right? This is an $8 billion project spread out over a decade to get exascale computing so that you can do this, right? And the goal here is to build an autonomous laboratory, a self-driving laboratory, where the sort of questions and the ways that those questions are investigated and the answers themselves are sort of farmed by silicon. And so the picture is really one of agents and instruments. I mean, at the end of the day, that's what this is, right? You have like artifacts, human-made machines, and then you've got people that are kind of working together. This is like whatever Dali says this would look like. I love that they're all at a computer. Okay, so what I want to argue for today is something like agents can work together with their instruments, where the collective, the group, is able to generate scientifically justifiable claims. I'm setting knowledge aside for the moment, because I want to use justified, but I don't want to use belief. And because I'm not going to want to ascribe beliefs to telescopes and microscopes, but I am going to want to ascribe, if this goes well, I'm going to want to ascribe knowledge to them. Okay. There's a quite large literature on how groups make science. This is the Atlas experiment at CERN. This experiment is so big it has its own Google map with Street View inside the facility, so that you can navigate the experiment. This is just some room where people control various aspects of the detector. This is not the beamline room, which is another room where they control the magnets for the for the beamline to accelerate the electrons. Literature has kind of grown up out of the investigation of large teams doing science, right? So Karin has this wonderful book, Epistemic Cultures, where she tentatively, and Ronald gives her a hard time for this, she tentatively ascribes knowledge to the experiment, right? And the reason for this is the story that we've heard, which is that no individual in the experiment knows everything or knows even enough to justify the experiment as a whole and the claims that are made of it. And moreover, knows how the rest of the experiment even works. So that even the PI on Atlas, if you can imagine that there's one PI on the Atlas experiment, knows how the beamline works or how whatever's going on in that room works. And nevertheless, able to publish a paper with some justifiable result about the Higgs boson. In this work, Ronald says, you can have distributed cognitive systems, right? So the cognitive labor is distributed over the system, but he's unwilling to sort of ascribe to the system something like knowledge. So you can distribute the cognitive labor in the way like Hutchins does with the pilots are sort of trying to figure out the airspeed of their airplane. Well, it takes like 3 people to do that. Claims that the cockpit actually knows the airspeed, or piloting a large vessel into port, right? You need people on the deck sort of taking relative measurements of landmarks on the shoreline. And then this is all sort of collated or additive. It's put up to the ship's pilot or captain, who successfully puts the thing in. And then Alexander, not just in this book, but in prior work, just comes out and says like, yeah, let's just ascribe. And it's unbecoming of a philosopher to, when the other philosophers in the room say what they think. I think he ascribes. He just wants to say that the experiment knows things. And I think that he's committed to the view that artifacts in the experiment know things too. That's going to be the thing that I argue. So this kind of process is given a lot of different kinds of labels. You can say distributed cognitive systems, and then you don't have to be so worried about ascribing mental states to things. You can say distributed cognition, and you might have to worry about whether you're ascribing mental states to things. And then you can say collective cognition, which I think is just like synonymous with both of those. Now we have a mature body of epistemology that helps us sort of think about how scientists justify their results from instruments. And we have a mature body of epistemology that helps us sort out how scientists get justification from other scientists, right? This is just like scientific testimony, and the other is sort of like instrument knowledge. And you kind of need to get these things to fit together to do an epistemology proofs. And so to do that, I want to focus on justifiable results from computers, and then I want to build up to the group. Okay. So this is just a logic diagram for an old Stalker computer. That's just like the logic board for it. This is physical instantiation of a logical procedure. So I want to argue the computer's a procedure. And I want to do that by looking at this proof for the 4-color theorem. So the 4-color theorem is this idea that any planar graph, and I'll say what a planar graph is in a minute, but any planar graph can be divided where each of the nodes in the graph are separable by some region, can be divided and then colored with at most 4 colors. It's a very hard conjecture to prove, but any configuration that's planar. So here's an example of 2 planar graphs. What makes it planar? It's just that these edges don't cross. That's the simplest way to think about it. They never cross. And so any configuration, as many nodes as you want, as many vertices as you want, right? That's edges going into it. If it's planar, you can color the nodes such that no adjacent node shares a color with with no more than 4 colors. This is not a planar graph. The edges cross each other. Here's a fun planar graph. That's the United States, right? So the borders of the states are such that they form a planar graph. If you have something like Vatican City, which is sort of sitting inside of a border, what you actually have there is torts. So that's colorable by 7 colors. But this, and we forget about DC. So the United States is a planar graph, and you can color it with no more than 4 colors. I mean, you can color it with as many as you want, but you need no more than 4. So to prove that all planar graphs can be colored with as few as 4 colors, the important thing is going to be the computation. But you start by showing that for any graph, if that graph were a counterexample, right, a planar graph that could be colored with, that needs to be colored with more than 4, then it must contain, it must be built from one of a finite set of specific configurations known as a reducible set. The details here are not important, but it turns out that there's a finite set of configurations such that the vertices and the nodes are arranged such that these are the only possible sort of examples that come to mind a priori that would require more than 4, maybe. And there's about 1,500 of these. And so you do a body of mathematics to show what these are, but then you need to color them, which is to say that you need to see if you can color them with only 4 colors. That's just the way that this proof works. And if one of them requires more than 4 colors, then you have a counterexample, and the conjecture is false. But if you can color all of them with only 4 colors, then there are no counterexamples. This is a priori. There are no counterexamples, and the conjecture is a theorem. So to do this, you have to actually color them. But there's 1,500 of them, and these configurations are massive. They're not like these. And so you need a supercomputer. This is a Cray 2 from about the era. This is like 85. The paper's from 89. So it'd be on something like this at the University of Illinois. And you just give this thing all of your graphs, and you say color them in accordance with this procedure. And so it's almost like a brute force check, right? You just start to color the nodes. And it outputs its results in about 500 pages of this microfiche. And so the worry here is that what is this thing? Get out of there. Go away.
Now go to more and then hide it. If you click 3 buttons and hide video and hide video. Oh yeah, that was
okay. So the philosophical worry here was that what had happened in this proof was that we had in fact introduced empirical considerations into something that was supposed to be a priori. Mathematical proofs are supposed to be a priori. The justificational force of a mathematical proof is a priori. It's not empirical, right? And so the worry, I'll just read this. The purpose of these remarks, this paper, is to raise the question of whether the 4-color theorem is really a theorem. The investigation should be purely philosophical, since the mathematical question can be regarded as definitively solved. Right? So it's definitively solved that that you can color all planar maps with no more or no, whatever, with fewer than or colors. That's definitively solved. The question is whether or not it's a theorem. It is not my aim to interfere with the rights of mathematicians. They have rights. They have rights to do mathematics as they would like. It is not my aim to interfere with the rights of mathematicians to determine what is and what is not a theorem. I will suggest, however, that if we accept the four-color theorem as a theorem, we are committed to changing the sense of, now here enters the philosophical scare quotes, theorem, or more to the point, to changing the sense of the underlying concept of proof. He uses quotation marks there. So by raising the question of whether the four-color theorem has really been proved, I will be trying to elucidate the concept of proof and not attempting to evaluate the mathematical work. His worry here, his worry in this paper, is that the computer's solving, or I'm sorry, the computer's coloring of all of the maps, all of the graphs, is an empirical process, right? Our justification for belief in the results of the output of the machine rests on empirical limits, right? Our understanding of the workings of electrons, our electrons through a sort of circuit board, our understanding of how the computer works, and then our sort of intuitions about their reliability in general. And so a little body of philosophy sort of sprung up in wake of this. We've got Luker, Detlefsen, and Luker, and Paul Teller. And Teller sort of characteristically is completely dismissive of this concern. Completely dismissive. Says this is as a priori as it gets. Never mind the fact that a computer solved it. His argument is not good, and I won't rehearse it. But it's basically like it's just carrying out a procedure. It's like you could do it in principle, and you can hear von Frossen in the background, like, well, you know, is the Statue of Liberty in principle portable, in the sense that, you know, something could hurl it. But Tyler Burge, writing like a decade later, actually puts together a coherent defense of why this is a priori. Though it's very, you know, it's in the style of Burge, so it's kind of hard to read. But the basic force of it is that, look, your reasons for thinking that the computer is reliable might be empirical. But the force of the justification for the proof is a priori. Right? So the computer could make a mistake. It is feasible. Just as a mathematician, sort of in writing out a proof, could make a mistake. And your trust in the reliability of the mathematician is just based on their prior reliability, right? They've proved many things. They know lots of math. They're an expert. They've published. They can make mistakes. They can misplace some things. But the force of the justification for the proof, for the theorem, is still an a priori procedure. So the in principle thing kind of goes through. Now, a couple decades later, this all comes about again in thinking about simulations. Now, simulations do give us empirical reasons, and so philosophers got worried again. And most notably Humphreys and Roman Frigg, Julian Rees published this. I had like this title: "The Philosophy of Simulation: Hot New Issues or Same Old Stew." And the argument that they make is that, look, we don't need to worry about the justificational force of a simulation on the grounds that it's opaque. Right? So Humphreys was worried about the opacity of simulations, and they give reasons to think that, I have 5 minutes, shoot. They give reasons to think that that it's not opaque, right? You know what procedures it's executing. And just so long as you know that those procedures have been implemented in the computer in a reliable way, which you have every reason to think, then the computer will execute those procedures. Whether the procedures are the right procedures is the thing you need to worry about. But if it's actually sort of carrying out the numerical simulation in the way that you deem that it should, then this is going to go through. So imagine if the four-color theorem were relying on today's neural networks, right? What would that look like? So today's neural networks don't like color maps. They might do some discrimination, right? That you might input a map and it might output, it's four colorable, or it might output, it's not four colorable, right? And you might do that for all of your maps. But the problem is that this doesn't tell us why it's a theorem. It doesn't actually color the maps. It gives us instead a probability distribution that it gives us a probability distribution over maps, right? It might say something like, this is probably four colorable. This is probably not four colorable, right? That would be an empirical consideration. And I liken this to Ramanujan, who's a famous Indian mathematician with very little formal training, who has a notebook full of conjectures, and then like 2 or 3 lines of mathematics, claiming that it's a theorem. And it turns out that most of them were in fact theorems, and that Ramanujan had sort of intuited the proof for these, but the proof is not inspectable. There's no way to actually see the proof, right? You need to ask Ramanujan, and he doesn't really know how to tell you what the proof is. And this is rather like what you imagine that the AI would be, right? They're not inspectable, you don't know what's going on. It tells you it's a proof, but this doesn't really count, right? This doesn't, the a priori force still is somehow like, well, the AI has done well in the past, right? But the past considerations of the outputs of a neural network would never justify something that's a priori, right? That's an induction. That's an amplitude inference. That's not a deduction. I've pointed out that you can reliably use these networks to guide mathematical intuition, right? So if you're trying to solve problems in low-dimensional topology, and you want to know how certain aspects of geometry are connected to certain aspects of algebra, you can use a neural network to sort of get salience on like what geometric properties are related to what algebraic properties. But then you still need the human to kind of work out how that all hangs together and get you a theorem. And this has actually been shown in this recent paper, which I know our next speaker is actually going to talk about, advancing mathematics by guiding human intuition to AI. Now, I still think the justificational force here is coming from the human, not from the AI. The AI is aiding in sort of directing intuitions. But now I'll just come to the meat of this. Imagine you want to prove something like the four-color theorem, but you have generative models. So generative models are different than Ramanujan, right? Ramanujan tells you it's a theorem. Ramanujan's like our vanilla deep neural network. The generative model will output a proof. So a generative model outputs a proof, which you can check. It's directly inspectable. Proof might be really long. So here's the thing we want to build up to. The process of discovery is completely opaque here, just like it is in the neural network. We're super worried about it in neural networks. Process of discovery, how the generative model comes to the proof is not inspectable, but that's okay, because the reasons for the proof are fully inspectable, that it outputs the proof, line by line. The justification is a priori, because it doesn't matter how it got to the proof. What matters is whether or not the sequence of lemmas and premises actually are justifiably deductible, right? That's the justification. And the generative model can output that, right? And we certainly don't want to ascribe beliefs to it about, I don't think we do at this point. And so when we reimagine this situation with generative models, what you get is a human and their generative model, and they give it something like this. This is me and GPT. I want you to do a simple multi-step task. First, I want you to put some Python that generates 1,000 random variables or values for 6 variables. Then I want you to write some Python that evaluates the correlation between those values. Next, I want you to write some Python that reports those correlations, generates a figure to display them. And finally, I want you to run that code to give me the output. And so it does that. And you might want to like check to see if that really works. And here's the code that it gave me. And I just run it real quick. And there it goes. Does the correlations, there's the correlation matrix. And then you say something like, okay, next I want you to write a very short paper about this exercise in LaTeX. Here's the LaTeX, right? and then you throw that into overleaf, let it render. Yep, there's the paper, okay? And next and then maybe you just want to publish that. So there's the submit. Okay, so far, all I've done is say, I want you to do this exercise. So then here's the fun part. Think about this, that was empirical, right? And all the empirical results are justified because all of the processes by which I arrive at them are right there, the transparent, fully inspectable. Imagine this in the a priori case where I want you to give me a proof. Well, that's fine. I feed it to a proof checker, which is totally justified, right? We use these all the time. Now, these don't really work when humans are giving the proofs because we kind of jump over huge blocks of mathematics, but that's fine. I can make this thing as verbose as I want, right? Give me every single lemma all the way down, check it, check it, check it, check it. And then there's the paper. So then I was like, now create your own prompt for an exercise very similar to the one I gave you. It does that. And then I said, do your own exercise. And of course it does that in exactly the same way that it did mine. Right? It generates the code, it generates the LaTeX, everything runs. And so the thing that I want to take away is that you can imagine this scenario here where the human gives a push, right? Kicks off this cycle, and you result in this. This guy never looks at that paper, right? Never looks in this process, never checks this. I just showed you that you can set this pipeline up really easily on your own. I want to claim that this is a priori knowledge. This is a priori knowledge. Nobody's ever seen it, right? It just got uploaded automatically to the archive. And so I want to say that mathematics knows whatever this theorem is. And no mathematician has looked at it. And that this is the result of a collective, namely a generative model, and a proof checker. Yeah, that's my talk. So